Good afternoon. My name is Jussi Pakkanen, and I'm here to talk to you about build systems, specifically the Meson build system, of which I'm the main developer and project leader. So the Meson build system, if you put it in a nutshell, it's basically a build system for multiple languages. C and C++ are the main ones, but we also support a bunch of other ones. And we optimize for the needs of today and not from 80s. So if you're running HPUX from 1989, you're probably not going to be happy with our thing. It could work, but it's not in any way guaranteed. Our goal is to be fast, lean, and efficient. And spending resources, or like CPU resources, on the build system is not very useful because they're better used when running for the compiler. Our goal is to be scalable, so we need to be scalable for tens of thousands of files. Like the rough goal is that we need to be able to scale to those sorts of things which you can compile on a single machine. So something like on the size of Chromium, it should be usable, it should be snappy, and there should be no lagging. We are kind of like the opposite of an IDE or a social network, is that we want you to use as little as possible. You are much more productive doing something else than writing build definitions. So we want to minimize the time you have to do that. And the build definitions that we have are, it's said to be simple and readable and not Turing complete. And this is by design, and we're not going to add Turing completeness ever. Well, this seems all fun and good, but when I talk to people about this, they'll always say, well, is there someone else using it? So let's see. Here's a screenshot from Fedora Linux, and there's a file viewer and the thing there. So if you click on that, then what happens is that it opens up this video player and shows you the video. So this video player application is called GNOME Videos. It's being built with Meson build system. The videos are being played with a multimedia framework called GStreamer. It consists of hundreds of plugins, also and H.264 and all that sort of thing. And this can also be built with the Meson build system. The file manager you see in the back is called Nautilus. It's also built with Meson. There's GNOME Shell, which is the thing that takes care of all of the windows and all of the logins and so on. The GTK widget toolkit, which is the default widget toolkit on Linux, starting with version 4, which is upcoming, is going to be also built with Meson. There's the X server itself, which is also buildable with Meson. I'm not sure if they have that upstream yet or in master, but it's buildable. Then there's the Mesa 3D, which is the 3D graphics driver subsystem. So the Vulkan implementation, OpenGL implementation, all the drivers that are part of user space, those are all buildable with Meson, and they're going to drop their old one soon. And then there's systemd, which is what most people call is the one process which takes over all of Linux eventually. But we have managed to take over it first, so it's buildable with Meson now. So it's used a fair lot in the open source world. There are proprietary projects. Unfortunately, companies usually don't really tell about them, but based on indirect measurements, we know that this is being used in lots of different commercial companies. For some reason, especially much for embedded. But let's get into actual compilation of code, because that's what we're here to talk about. So let's create a very simple Hello World project from scratch. So here's the screenshot of a terminal, and we run Meson and give it the init command, which is kind of like the git init, and then we specify that the project name is going to be CppCon. Then -l CPP means that the language it generates should be C++. -b means that it should also build the thing in addition to creating it. And type executable means that we have to create an executable as opposed to a simple library. So then it runs this. And you can see it's creating a new sample project, and then it runs and builds. And you see it's using GCC 8.1, which is the default compiler on the Fedora installation that this was being used for. And then it builds and it links. And if you run it, then you get output of this is CppCon. So you can go from nothing to a project which builds and runs in about 2 seconds. So let's look at the build definition next. I could explain to you, but I'm going to instead do something else. So I'm going to give you 10 seconds to just read through the build definition file. It's going to show up soon. And then we'll go from there. So you're going to have 10 seconds starting from now. Okay, and time. So based only on this 10 seconds, and you've read through this, how many of you would say that you understand what's happening here? Okay, like, just raise your hand if you think you understand what's happening. Okay, for the viewers at home, that's almost everyone in the room. So this is what we mean by readability. There's no ampersands, there are no dollar signs, or anything like that. It's fairly readable. You have a project, you have a C++ version, and you create an executable with one file, install it, and then there's a unit test for which you define as called basic. It's fairly simple. But this is actually quite powerful because just with this, you can get a bunch of other things. So let's go through those. So first of all, you get the different build types. This is kind of like what CMake does. You have a debug build, you have an optimized build, all those sorts of things. There's a language standard flag, which you can use to select like C++ 14, 17, 11, whatever you want. And it's automatically applied to all compilations. There's a test suite runner. So you just define your test, and you can run a test command, and it will do all that. And it will automatically run all of your unit tests in parallel. And you can tell it that like certain tests can't be run in parallel, and that's fine, you can do that. Then you can also get coverage reports, and you don't have to copy lots of text from one place to another and try to find Stack Overflow. There's a simple options like, I want to have a coverage report, and then you just you compile, run your test, and then say generate the report, and then it's done. And you don't have to worry about that. There's a warning level toggle. Who of you enjoy writing the thing where you have W all in some compilers and -W3 or something on this Visual Studio? Well, it's not really interesting. So we have warning level toggle that automatically takes care of this for you, and you can change that without having to change the build definition files that you have. We have native Unity build support. So in this case, there's only one file, so the Unity build file doesn't really help. But yeah, there's a toggle for that. Just toggle that, and it builds every file that you have, every project that you have in Unity build mode. There's native precompiled header support. You just need to write your precompiled header file and say, I would like to use this precompiled header for this target, and it will do all of the magic necessary to make it happen. Cross-compilation support, native out of the box, you don't have to do anything in this particular case. You just tell it, I want a cross-compilation to this target, and then it does that. Link time optimization and profile generator optimization, toggles for that, you just enable them if you want to. Sanitizer support, so address sanitizer, memory sanitizer, all of those things. If the compiler that you're currently using supports the sanitizers, then there's a toggle option where you can just say flip, and now it's on. Scan build, which is the static analysis tool that comes with Clang. There's full support for that, so if you have that installed, it will automatically generate for you a target called scan build, so you can just run it, and then it will do all the magic necessary to generate the thing. This was landed a few weeks ago, so there's your selection toggle for your Visual Studio runtime. By default, it matches what your build type is, but if you want to specify, okay, I want to use the -MT, then you can do that. There's one toggle option for that, and you don't have to put it in your build definition files. And also, this is a bit of an interesting one. So Meson has a thing where if you build shared libraries, and then executables that link against them, and then you change the implementation, but not the interface of the shared library, then when you rebuild, it will automatically skip relinking for all of the executables. And there are people here, probably in this room, who think that like static linking is the best thing ever, and that's the only thing anyone should ever do. And like, why would anyone ever use shared linking? Well, one of the reasons being that if you do this, then you have incremental builds which are 10 to 100x faster, which is kind of nice, especially if you're like one of me who don't have a spare data center to run your compiles in. So, but that was building. And building source code is actually the easy part. What's hard are the dependencies. And a good question is, why are dependencies hard? What is the thing that actually makes them difficult? And what makes it difficult is that there's so much variability. If you have a large project and you have lots of things happening, typically what you have is that you have a big project and it composes of lots of small projects, sub-project dependencies and so on. Some of those are internal. So you have people in your organization working on some library, and you want to use that. And then there are external libraries from the open source community that you're probably all using. The dependencies can come from the system, or that you can build them yourself. If you insist on building your dependencies yourself, and you want your software to be included in the Debian, you're going to have a bad time. And on the other hand, if you just use what Debian has, you're going to have way too old dependencies, and it's going to be tricky to do. And so you really want to have both. Your dependencies might be shared libraries, they might be static libraries, they might be header-only libraries. You might have a monorepo. You might have Git submodules. You might have not Git submodules, but instead many Git repos and a script that puts them together in magical ways, and then you can compile. Your dependency might be in tarballs, because it's specified that you can only build from these blessed specific releases and not from anything else. And diamond dependencies are the things that make these things interesting, because if you have some sort of dependency that's being used from two different places, you really want them both to use the same one, because this is not Node.js, but this is actually like you have to get rid of all these duplicate dependencies, because otherwise you're going to have a very bad time. And usually if you have a big repository, there are multiple things that you want to produce out of it. So if you're working on games, you might want to produce different games which share most of the code, but some parts are different, and you want to toggle between which one you want to build. Or maybe you provide something like firmware or something like that, where you need to build different things for different hardware platforms. And depending on what you're targeting, you build different things and you have different dependencies. And then you have, usually most projects have options where you can toggle things, as like whether you build with some backend or some other backend. And these are usually shared, so if you have many dependencies, it might be that one specific thing is shared across 5 different sub-projects, but not any of the other ones. But then there's another dependency which is shared among some other ones. And it gets very complicated very fast. And this was the easy part. So for extra bonus points, when you are developing on a big project, and especially if you have a monorepository, what you really want to do is you want to only focus on a very small subset at a time. Like if you're working on a string class implementation, you really want to only have your string class and nothing that depends on it. Because if you need to rebuild the entire world every time you do a change, it doesn't really work. And if there were people here thinking, it's like, yeah, but I can just manually make my target because I know that it cannot affect anything else, don't do that because it's going to break. And experience has shown that this will always break. So we really want to have some sort of tooling support to make this simple and easy and workable. So let's look at this in a graph form. This is a simplified version of what the dependency tree might look like. So you have a bunch of sub-projects which have dependencies between them. And then you have build options, which are somehow going like this. And then what you want to do is build that one thing, but nothing above it. And then this dependency must come from the system. These are the things that usually come up. It's like, this is a thing that you have to do. And then it's like, well, how do I make that happen? And this usually gets very difficult. So, what if I told you that in Meson, we support all of these cases using only 3 primitives? If you don't believe me, raise your hand. Okay, there are some people who are skeptical. Okay, so let's go through that. So perhaps the main thing we have is that when you build a sub-project, it's built as a sandboxed separate entity. So it cannot access anything outside of its own world. This is different in CMake, where you can just add a subdirectory, you can go inside of the other one, and then they can change your global state. And in Meson, this is not possible. We prevent you from doing that, and you have to do the very isolated build. So all of your sub-projects can be built in isolation from each other. The second thing is that in Meson, dependencies are objects. And an object encapsulates a way of how the dependency is provided. So it might come from the system, and it might come from a thing you built yourself or from wherever. But when you have a dependency object, you don't care. You can just put it in your targets and say, use this, and then the system will take care of putting everything in. So this is kind of like a dependency object which has many different shapes. So it's kind of like a multiformic dependency object, if you will. And the third one, this is a bit esoteric, but the project options have a way of specifying a thing called yielding. So if you have a dependency which has an option with a specific name, that subproject can say that in the event that I'm being built as a subproject and the master project has a dependency, it has an option with the same name, then instead of returning my value, return the parent one's. And in this way, you can enforce that the option values are same across all of your things, but if you build any one of these in isolation, then you can just toggle the option for that one. So looking at how this would look like if you have a dependency added, so the things that are added are in yellow compared to the ones you saw earlier. So the interesting line here is the first yellow one, where we are using a Lua dependency on our project. So this is the very common Meson nomenclature for saying that I want a dependency called Lua and try to find it from the system. And in the event that you cannot find it from there, then build it as a sub-project. It's in a very specific place. And then return the dependency object from that one. And then after that, the dependency object at runtime will contain either the system dependency or the one you built yourself. But for using it, you don't have to care. You just put it in the target where you want to use that, and then all of the magic happens automatically. So this is kind of like a pull model where you don't have to build everything, all of the dependencies in advance. You can just start from the bottom and say, like, I want to build this, and then they will say, I want this, I want this, I want this, and then the system will add them as needed, and you get only the minimal stuff that you need. And once you have this, then you can now build your thing. You can build any subsection of the entire project structure. You can take any thing and say, like, I want to build that one, and it will only build that and the things that it depends on. Any dependency combination, if you want to get this from the system, you want to build yourself, you can toggle between them in any way. And the important bit is here. You don't have to change your build definition files in order to tell you where the dependencies are coming from. There would have been a live demo. This is only a 30-minute presentation, so it has to be skipped, unfortunately. But it would have been great. Onwards, which is the Python thing. So Meson is implemented in Python, and this is a sticking point for many. So the common thing that people say is that the C++ build system and package manager should be implemented in C++. So who here agrees with this statement? Okay, there are lots of hands. Okay, so let's go with this. So the Rust build system and package manager should be written in Rust. Who agrees with this? 2 guys. Okay. The Go build system and package manager should be implemented in Go. Who agrees with this one? Same people. The D build system. Okay, so you get the point. Can you spot the obvious problem with this? I see the CMake maintainer nodding. Anyone else? Yeah. So this actually has been spotted quite a long time ago by a person we all know. So this is a quote from Bjarne saying that anyone claiming to have a perfect programming language is either a salesman or a fool, and probably both. So the big problem with having a single language build system and Dependency Manager is that each one of them is a silo. They isolate you from there. So if you get into one ecosystem, it's very hard to work with other ones. But being what the world is today, a single program language is just not the best thing for everyone, even for C++. As an example, some things that you might want to do is that if you have a crypto library, you might want to have it written in Rust, because that's where Rust is at its core. You really want to have all of the possible power and security that you want, and you would want to combine those two. So the thing is that if you have a project which has many different programming languages, which is quite common these days, then the thing is that not any one of them is going to have a build system and package manager written in itself, because you really only want to have one build system and one package manager in any one build directory. If you have more than one, it's going to fail. There are lots of people who desperately want this to not be true. Unfortunately, it is. Sorry. But in Meson, we try to approach this in a different way. So the design we have is that you should be able to mix and match languages completely freely. All of the languages that we have, they should just work together seamlessly, so that you can pick and choose the best thing that for you. So let's build a Python extension as an example. And in this Python extension, we're going to have C, well, obviously, because that's the language that the Python extension modules need to be, C++, Rust, and Fortran in one single shared object module. So the code for this can be found in the GitHub address shown. And so let's spend, I'll see, I have some time. So think about all the people here in the room. So think about how many lines of code would you need to write in the build system that you're currently using to make this happen. So 4 different languages, and you need to pull a Python extension. Okay, so let's see how many lines of code it takes for Meson. So, all right, ready? 1, 2, 3, 4, 5, 6, 7, 8, done. And this is all you need to write. And this is, at the end, this is what Meson really is all about. The conceptual model is very similar to SQL. Your build definition file should explain what you want to happen. It should not have to explain how you do these things, like all the steps you need to do. It's just like, this is what I want to happen, and then the system takes care of it for you. Because I don't know about you personally, but I really don't want to spend the rest of my life babysitting compiler flags. I just want to do stuff that's actually useful. Since I have some minutes of time, there's a hidden round because there was time for extra slides. So we added Lua to the sample project. So let's now look at how you would do the package management and download part. So you create a directory called subprojects, which has all of the dependencies have to be in this particular directory name. And then you issue this command. So wrap is the command that we use for downloading dependencies from a service that we have called wrap database. And it consists of the upstream tarball and then Meson build definitions that we have written and which people can contribute, and they come together to build the thing as a dependency. So this then does the web calls to get Lua 5.3, which is the latest version available in wrapd at the time. And then you just start building. And here we see that it couldn't find Lua from the system, so it then downloads it from the lua.org website. And then after it's done that, it downloads the patch file which contains the build definition files from the wrap database. And then it starts executing that, and then it configures to Lua and compiles it and all of that. And then compiles and links, and that's it. And that's all you really need to do to get your dependencies downloaded from the internet. And this is not directly tied to the service that we run. If you want to run your own, go for it. But this is how you would manage download dependencies automatically on all platforms that support that. There are 5 minutes left for questions. If you have any, please queue at the microphones.
Hi, quick question. You support or are thinking of supporting distributed builds and distributed cache?
Okay, so the question is, are we supporting distributed builds and distributed cache?
Distributed over multiple machines.
Okay, so we already support it because there's Ice Cream and there's Ccache, obviously, which are fairly good. So I wrote a blog post about this, and then like, how would you replicate the build environment that something like Google has, where you have tons of different machines and you want to spread out. And it turns out that, at least according to the test that I ran, the thing that is actually difficult is the distributed file system. I was using NFS and it just completely fails at this. So if you want to do a proper distribution, then what you have to do is that you cannot pre-process on the machine that you're building on, because then you're limited by your own machine. What you want to be able to do is to farm out all of the commands out. And for this, you need standardized standardized containers and an NFS or something like that, which you mount. And the NFS seems to be the problematic part. So if there is a project to add, to create like the backend service for running these sorts of things, we would support that. It's not that difficult, but getting that to work is the hard part. And it's not really in the build system as much.
All right, thank you.
So as a Qt user, so I use CMake and then Qt, and we have this find Qt and Qt chips, Qt5 chips with CMake files. So, and I've built Qt myself, or I have pre-compiled Qt versions. How would I go with Meson here?
Okay, so I'm having a bit trouble time hearing, but you were asking about Qt.
Yeah, right.
Compiling Qt yourself.
Yeah.
Okay, so I know of people who were interested in building Qt, and on the other hand, the Qt people are currently talking about changing their build system for Qt 6. I had a chat with one of the people running this, and they had a list of requirements of what you would need to have in order to be the official build system of Qt, and we have like most of those we actually do support, so it should be doable. But as of today, you don't build yourself. But if you have pre-installed Qt and just want to use that, then we get all of the dependencies from QMake directly. So it works on Windows, it works on OS X. I don't know if it works on iOS or Android. I don't think anyone's ever tried that. But it on Linux, on Windows, those all work.
Okay, thank you.
Okay.
Yeah, I was wondering, how would you incorporate new static analysis like CppLint, where it depends on each of the source files in a target?
Okay, so the question is, how would you add CppCheck or other kinds of linting tools? The Meson has a concept called a run target, and you can specify that I have a run target with a specific name, and it runs this command. So you can, and then you can say ninja the thing that you want to run, and it will just execute that command. So you would probably have CppCheck and then point it to the compilation database file. So you can do that yourself. We don't have any built-in support for that because it's so simple to add yourself. And usually once you have your own special flags, so this it wouldn't really help to add more stuff. But if there's like complicated tools, then we would probably add support if needed.
Okay, thanks.
So I have 2 questions. The first is, do you support auto-generated files like those generated by Protobuf or not?
Yes, we support. So the question is, do we support auto-generated files? And yes, we do support that. And starting with the release that we did a week ago, what you can do is that if you have a Protobuf thing, you can compile Protobuf as part of your project, and it will use that built executable to generate the Protobuf files without you having to change you just say, I want to find Protobuf Proto-C, and it will find the one that you compiled yourself. So you could have fully self-contained build
So kind of connected to that, my second question is, do you have anything like CPAC that aids you in the packaging side of things? Because the difficulty with all of the systems that bring in loads of tarballs is then it becomes a bit of a nightmare to actually package everything up.
Sorry, can you say?
So do you have any infrastructure like CPAC, which admittedly is pretty abominable to use, but do you have any infrastructure that integrates with Meson in order to aid actually generating vendable binaries from your build system? Or is that out of the scope of Meson?
So the question is, do we have something to generate vendorable binaries? Okay, so not as such, but if you build all of your own dependencies, and you link them and you install them, and then in somewhere, then you tar that up, and then you ship it. If that's fine for you, then it works. Like if static linking all of your dependencies and just ship the executable, we support that, but there's no like specific support for that.
Okay, thank you.
I have a few quick questions. What's the IDE support for things like CLine, Kdevelop?
Okay, so the question is, what's the IDE support? So currently there are 2 IDEs which support Meson project, because we ship an IDE like introspection framework. So we expose all of our data in JSON, and no builder supports this. And starting with like 6 months ago, the Eclipse upstream had support that. So it has native supports for Meson projects, and you can change all of the options and all that sort of stuff. There was going to be one for Qt Creator, but that got cancelled due to reasons. The CLion doesn't have support. I actually chatted with Phil Nash just prior to coming here, and if you wish to have this support, please go up to the JetBrains booth and tell them that you want this. It's not going to happen otherwise.
Thank you. And what other languages are supported?
So which languages are supported?
Yeah, you said it's multilingual.
Okay, so the final list is up on the website, but C, C++, Objective-C, Objective-C++, Java, C#, D, Rust, Vala, and Fortran.
And the question related to earlier, like code generation, is it generic or is it Google Protobuf specific? Can you build up something like for your own code generation?
So the question here was that is the way of, if you generate source files, is that specific to Protobuf or is it general? It's completely general. And in fact, we don't have any sort of Protobuf specific helpers. We might add if there's need for that, but it's completely generic. You just specify, okay, this is how you would generate files, and then you put in the inputs, and then you just put the outputs in the target you want to use them in.
Thank you.
Okay. I think it's the last question.
All right. I guess follow-up question to the IDE question. I was just wondering, what's the interface that you expose the compile definition and stuff like that? So, for example, I'm using, let's say, Emacs, and I would like to kind of hook into that. How would I do that?
Okay, so we generate the compilation database.
Okay.
So that's there, and then, but that's just like the things used to compile files, like the flags and everything. But the IDE, so the JSON-based introspection thing, you can get all of the options, you can get all of the tests. So as an example, if you have a test that is failing, you can actually get all of the things that you need to run it yourself, like the command line, the environment variables, you can set all of that. You can get what targets are there, what source files they contain, and all of that. So you should be able to add that in.
All right. Thank you very much.
All right. So I think that's time. Thank you very much.